This lesson is the second part of 3.1b. It's about the second law of thermodynamics. In every energy transfer, some of the useful energy becomes unusable and increases entropy. So in cars, for example, 25% of the gasoline gets converted into kinetic energy. In cells, that is about 40%. The rest is lost as thermal energy. And thermal energy is not considered something that can do work. This inefficiency results in an overall increase in entropy, which is a measurement of disorder. And all systems in the universe tend towards disorder. For example, even if you put a lot of effort into tidying up your room, it always tends towards messiness. At the level of chemical and physical changes, this increase in randomness happens when you have large particles broken down into smaller ones, or you have particles spreading out. In terms of living things are very highly ordered, such as arrangement of flower petals or the compound eye of an insect. Living cells can create order out of disorder, such as making proteins from amino acids or DNA from nucleotides. It is possible to maintain a low amount of entropy or low disorder, but it takes a lot of energy. And this energy could come from light or bond energy. So the first and second law of thermodynamics help us to predict whether a chemical or physical change can occur without a continuous input of energy. For one, a spontaneous reaction is one that will continue on its own once it's underway. So for example, if you were to light a match, it will continue to burn. There are non-spontaneous reactions that you have to continually put energy into, such as boiling water on a stove. If you took it off the stone, it won't continue to boil. If you go from a clean to a messy room, it doesn't take a special energy or effort, but going from a messy room to a clean room takes a major effort. A spontaneous reaction can be a slow one, like rusting of a nail, or a fast one, like burning of a match. In determining whether a change will happen, there are three factors, including energy changes, entropy, and temperature. Exothermic changes are accompanied by an increase in entropy or occur spontaneously. Whereas endothermic reactions, such as making a glucose molecule, does not occur spontaneously. So the change in energy, not the change in entropy, is favored since this change in order requires energy. So the second law of thermodynamics says energy transformation is not 100% efficient. Some energy is also lost to the environment. And the energy that's not lost is called free energy. So free energy is the value of a chemical reaction that provides us. The free energy value provides us with useful information about the study of metabolism. So here's our Gibbs free energy, your final state minus initial state. That can be calculated for every reaction. If an organism were to oxidize 1 mole of butanoic acid, it releases 470 kilojoules of energy. We know that the cell won't use some of that energy, and that will be released as free energy. That will be released as thermal energy. So looking at endergonic reactions versus exergonic reactions, you can see this one is like a rock that's on top of a hill. It can go down and be more spontaneous. Whereas one that's here, it's more stable, but it has less of a capacity to do work, and there's less free energy there. If you have a positive free energy value, then the energy of the product is worth more than the energy of the reactants. If you have a negative free energy value, then the final state of the molecules. So the difference is between the state of the molecules here versus here. So now there's less free energy. It's more stable, but there's less capacity to do work. In an exergonic reaction, such as this one, you can see that this is a negative value. That means that that's the energy that will be released. This is the oxidation of glucose. It releases free energy. Spontaneous once started, and free energy is released. There's an increase in entropy. There's more molecules, and yeah. This photosynthesis reaction is an endergonic reaction. Plants combine CO2 and water to create sugars through photosynthesis. It has a positive delta G value, which means energy is absorbed or has to go in. And you can see there's more complex products. Burning wood, etc. The ash has less free energy that can now do not very much work, and it's spontaneous. Whereas an endergonic reaction, like making glucose, you have to take energy in, energy is stored, and the product is more complicated. So here you have your reactants, there you have your products, and the products have less free energy. And then in the meantime, it's released that energy. Whereas in an endergonic reaction, you have things like CO2 and water, and you put energy in, and you can get a product like glucose. Sometimes cells are able to make these endergonic reactions go by coupling them with exergonic reactions. So for example, if you have this reaction, it releases some energy. This reaction, it needs some energy, but if you put them together, it'll actually make both reactions go, and with a little energy released afterwards. This is just a different way of showing the same thing. Looking at this, this is a catabolic pathway. Here, energy is released. Here, it's put in. And here, it's released. But overall, then energy is released. As opposed to this one, some energy is released, some energy is put in, more energy is put in. Overall, energy is absorbed. So the catabolic pathway is one where energy is released or broken. Things are broken down in order to release energy, whereas an anabolic pathway is where you're building something up. So I think of it in terms of anabolic steroids, for example. Those are ones in which you want to build up muscle, for example.